we come to our last paper of the evening. The title is Comparison of Failure Rates According to Secondary Circuit Configurations of Full Bridge Converters Using Fault Tree Analysis. The paper is going to be presented by Jae-Hun Cha. So, Mr. Cha, you can start.
Thank you, Chairman, for introducing me. Hello, everyone. I'm Jae-Hun Cha. I'm majoring in mechatronics at Gyeongsang National University. The topic I will present today is comparison of failure rates according to secondary circuit configuration of full bridge converter using fault tree analysis. This is summary before the presentation. In introduction, I will explain why I wrote this paper and why it is important. Next, I will explain characteristic of target converter circuit structure, failure rate analysis, fault tree analysis. Additionally, in comprehensive comparison, we analyze converter price through cost model analysis and also derive trade-off relationship too. Introduction. The motivation for writing this paper is to understand the characteristic of the converter that changes as the structure of the secondary side of the transformer changes. Among these, there are efficiency, price, reliability, and MTBF. MTBF is similar to product life. I will explain more detail on the next page. Particularly, predicting the reliability is very useful in the industry because it can predict the product's lifespan and prepare for potential failure in entire system. The following show is the type of converter to compare. For equal comparison, each converter have input and output are the same. And the converter have same circuit structure on the primary side of the transformer. However, they have different rectifying circuit structure on the secondary side of the transformer. First of all, type 1 is full bridge converter with full bridge rectifier. It has advantage of being simple structure to construct, but the diode voltage drop is twice as high as that of type 2. Next, in the case of type 2 is full bridge converter with current doubler rectifier. The transformation ratio is 10:2, unlike type 1. So the voltage applied to the diode is 48 volts. It's twice as high as that of type 1 diode. Also, these factors affect the reliability of the converter. Failure rate analysis. Before analyzing reliability of the converter, we should understand failure rate concept. So this page presents component failure rate calculation method and analysis criteria for the component used in the converter. The component failure rate was selected by referring to the military handbook 217F failure rate library. The first table is formula for calculating failure rate by components. So we can know each component has different failure rate factor because each component has a different factor that affect the failure. And then the table on the right summarizes conditions used in the reliability assessment. We operated based on 65 degrees and rated power was 1.2 kilowatts. And also each component quality was selected as lower, a commonly available component class. And lastly, the usage environment was GF grade, which means that its movement control environment environments such as installation in internet devices. Let's learn more about characteristics of component failure rate. The graph on the right shows changing in the failure rate of computer component with temperature. The x-axis mean temperature and y-axis failure rate. In component failure rate generally high in order of IGBT, diode, capacitor, transformer, and inductor. So from this, we can know that magnetic components have a lower failure rate, such as transformer and inductor. And in the case of transformer, we found the transformer failure rate increased rapidly from the hotspot temperature of 145 degrees. Additionally, we analyzed the failure share of part that fell in converter at 65 degrees. The blue section is IGBT failure share, and orange section is diode failure share. From this, in both types have a high failure rate of IGBT more than 70%. In the case of type 1, the diode failure share rate is more than 10% higher than that of type 2. So, it means the type 1 need to decrease the diode failure rate of diode. Next is fault tree analysis. The fault tree analysis is one of various reliability analysis methods, which is deductive analysis method that first define the top failure, and then divide the cause of the failure functionally. In this paper, the top level failure was defined when the rated output does not come out. And the table below shows equation for the logical operator of the FTA. When analyzing reliability, we use this logical operator. Next is fault tree. This fault tree is type 1 fault tree. The functional part were classified into 4 categories below and analyzed. And we analyzed why the function does not functioning normally up to part by part. Each converter, the type 1 and type 2 are primaries have same functionally in DC-DC converter. However, they have different circuits on the secondary side of the transformer, so the red square box section means the type 1 and type 2 configuration are different. It can be different because of the failure. And then we analyze converter failure rates based on temperature based on fault tree. Look at the graph. We can know generally the higher temperature get higher failure rate. And also at 65 degrees, type 1 has about 10% higher failure rate than type 2. This is because type 1 used more diode that were affected by temperature. The table below shows how much diode used each converter. Type 1 used 4 diodes and type 2 used only 2 diodes. This page shows reliability and MTBF comparison of each converter. Here MTBF is mean time between failure, which is average time between failures. It obtained here is the availability is 100%. The first graph is all-time reliability changing according time. The x-axis is time and y-axis reliability. We can see the reliability change decrease over time. Also, type 2 reliability appeared to be higher than that of type 1. Next to the reliability graph, there is MTBF graph. PDF graphs show they have difference about 2,600 hours between them. This difference is due to different circuit structure and different components being used. So, what I want to tell about is that even if purpose and capacity are the same, the reliability varies depending on the components and circuit structure used. The first thing I will tell you about in comprehensive comparison is cost model analysis. The cost model analysis focuses on actual cell components and based on component specification such as rated voltage and current and power using a trend line. So it's very useful when you want to know about product price, even component price, according specification. We only consider the price of essential components in the converter. As a result, the type 1 price about $22 and type 2 price was about $24. So the type 2 is about $2 more expensive than type 1 because 2 inductor with relatively high cost being used. We analyze trade-off relationship between voltage margin and efficiency and price by components. The first graph shows the price that changes based on the switch margin. The usage switch in the comparison are IGBT and power MOSFET. So the first graph shows IGBT is about 47% more affected by voltage margin increase than power MOSFET. The second and third graph show changing in converter efficiency as the voltage margin of switches and diode increase. Interestingly, in terms of efficiency, the power MOSFET is 27% more affected by voltage margin increase. Conclusion. We study changing in operating converter characteristics according to circuit structure and analyzing reliability of converters through FTA, fault tree analysis, and also derive a trade-off relationship according to component voltage margin increase. In conclusion, on average, type 2 provide about 4% more reliability than type 1. And when increased voltage margin increased by 0.1 time, we found on average the converter price increased by 3.6% and efficiency decreased by 0.2. Lastly, I hope this study can be helpful for reference during converter design process. Thank you for your attention.
Thank you very much. Very interesting. Thank you. We have time for some questions. Do you have any? Yeah, please give your name, please.
Thank you for presenting. Because I'm not quite familiar with this field. So
Me too. I am not very familiar.
So you mentioned the failure rate.
Yeah.
So is it kind of information that discrete component vendor provides in the data sheet?
We refer to military handbook 7F failure rate library. We refer. Military handbook 7F failure rate library.
So
We can see internet easily. It's open data sheet.
okay, data sheet. So kind of a failure rate for each component, capacitor, inductor, transformer.
Yeah. Also, we calculate component failure rates and we draw a graph by formula.
So in the first step of your research, you find that information as a reference, but when you apply those data I mean, when you verify whether type 1 or type 2 which is the best, then did you simulate some kind of equation?
Actually, we analyze more converter circuit about center tap rectifier, and yeah, but in the case of reliability, the type 1 is very low reliability. So the focus on reliability, the type 1 is less than other compared to other types. But we analyze volume and weight others. So if you focus on weight and volume, you better choose type 1. It's very lightest and least bulky converter. But if you focus on reliability or efficiency, you better choose type 2, like using magnetic components. Yeah.
They are more reliable. Magnetic components.
Yeah.
Can we have another question? Something? No. Please, something.
Okay. Thank you. I will start also by saying I'm very familiar in this field. So, can you go back to the factors that you use in the calculation? Yeah. So those come from this library, and probably it's based on statistics, failure, and testing, and so forth. But there is also a whole line of research of people working on reliability of power converters that look at the operation of the converter rather than just the components and some of the design parameters, right? So, for example, one thing I've read is that the temperature differential of the semiconductor is really very a big point, and that depends a lot on, for example, the modulation scheme or other kinds of controller-based things. So it's not just the hardware. So what is that in any of those factors included?
In military value direct library, there has many environment factor. So we choose, and the value is different too. So
But environment, does it means environment like humidity and stuff like that?
yeah.
But I mean, for example, when you have a modulation scheme to drive the switches, you can use different kinds of modulation schemes, right? And some modulation schemes will produce larger temperature differential in the junction, and other ones smaller. And so some research has shown that reliability increases if you have smaller deviations of temperature, and so this is favoring some switching, patterns that are more distributed rather than ones that are concentrated, things like that. So that it's more related to the operation of the converter rather than just the environment and the type of component. Is that an additional factor that should be added, or is it somewhere in between? Which
Probably, but okay. I know. I understand this question, and probably we should consider that additionally. Those aspects. He is talking about, due to the operation, the internal distribution of losses and temperature.
Yeah.
But I think you have not considered the operation, just the structure, the circuit, and the environmental conditions. Probably.
For example, the temperature factor, 65 degrees.
Yeah.
That's an average temperature in junction, right? It's not like
I get it.
that's the average.
The average temperature, right? The 65 degrees average time, but we want to follow the IEC operating guideline, but there is no information about 60 operating temperature.
Okay.
So
Okay, that's the environmental temperature. That's why you have -40 degrees.
Yes.
Yeah, but
That is clear. So I'm talking about another temperature, but we.
But it is clear. No, don't worry. We are clear.
We can analyze
Yeah,
other temperatures.
Yeah. Okay. If you have another question. Okay. Thank you very much for this. And with it, we conclude the session. Yes, I think.